Hello friends, now I am going to discuss about one problem where we can design an RCC member subjected to predominantly bending moment and low value of compression. This is the normal case encountered in the case of a framed structure. Here I am going to explain how we can design in such a manner that the reinforcement is correlated exactly as per the requirement. And we don't want to provide equal reinforcement, ASC and AST. Whenever the members are subjected to bending and compression, how the problem is dealt among the professionals, let us have a small discussion on that. Some people are using the design charts given in SP16, which are applicable for bending and compression. That gives equal value for compression zone and tension zone. There is nothing wrong in that, but the design is uneconomical. There are some people who are designing this only for bending moment and they are ignoring the axial compression. That is okay in the sense the structure will not collapse. However, ignoring the axial force is not correct. There are some people who are using integrated analysis and design program. These inbuilt design programs are giving value for compression zone and tension zone reinforcement differently. In that sense, it is okay. But it appears that they are designing the section only for bending moment and they are adding the additional reinforcement in compression zone and tension zone on ad hoc basis. Why I am telling this is each and every software provider is giving different values for ASC and AST for the same design problem. This gives an impression that nobody is following a standard design procedure based on the equilibrium equations of forces and compatible equations for strains. So I thought I will discuss this problem where the member is subjected to predominantly bending moment and low value of compression. And to the best of my knowledge, this problem is not addressed in IS code or SP16 so far, or even in textbooks. So first, let us go through the design parameters and establish the data required. The given section is 300 mm wide, 600 mm depth, coverage 60 mm on both tension zone and compression zone. This is ASC and AST to be calculated based on the equilibrium equations to be capable of taking these values MU 390 kilonewton meter and PU 170 kilonewton. Now we will use these, we will design this as a balanced section so that we are taking advantage of concrete compression area to the maximum extent possible. That is, we will assume the strain in the collapse status 0.0035, which is compulsory, and we will assume the strain in the tension reinforcement as 0.0042. This corresponds to FY 500. This is based on the minimum value of the specified strain, that is 0.87 Fy divided by Young's modulus plus the residual strain of 0.002, so that it will come to 0.0042. By assuming this strain values, this depth of neutral axis works out to 248 mm. As a balanced section, that is, once you assume these values 0.0035, 0.0042, this is a balanced section. Here the grade of reinforcement is Fy 500. Then for the balanced section, it is 0.46 times effective depth. Effective depth is 60 mm plus 480, 540 mm. And 0.46 into 540 is 248 mm. This is the depth of neutral axis. The proportion of the strain 0.0035 and 0.0042 and the proportion of XU and D minus XU is same, and that is how it comes to 0.46 XU. So XU is 248 mm. And what is the strain in the compression steel? At a distance of 248 mm, it is 0.0035 mm. Therefore, at a distance of 248 minus 60 mm by direct proportion, it works out to 0.0027 mm. This is the strain in the compression reinforcement, based on which we can get the value of stress in the compression reinforcement. Now, this is the strain diagram. Now, we will come to the free body diagram. C1 denotes the compression generated by the concrete. It is rectangular cum parabolic stress diagram. Extreme fiber stress is 0.45 FCK. C2 denotes the compression generated by the compression reinforcement. The external compression 170 kilonewton acting at the mid depth of the section. The moment 390 kilometer meter is acting in the clockwise direction, causing compression here. And this is the tension taken by the tension reinforcement. This is the free body diagram. Now let us find out the lever arm for various forces. 170 kilonewton, the compression, external compression acting at the mid depth of the section. Therefore, with respect to the tension steel, the arm distance is 248 mm. And the CG of compression generated by this rectangular cum parabolic stress block C1 lies at a distance of 0.42 XU measured from top. So here XU is 248. So 248 into 0.42, it works out to 104 mm measured from top. That out of total effective depth, if you deduct this 104, the arm distance for C1 comes to 436 mm. This is the arm distance for C1. Now, what is the arm distance for C2? The total effective depth is 540 mm. Out of that, you deduct this arm cover of 60 mm. So, for compression reinforcement, the arm distance is 480 mm. Now, we will proceed to calculation of equilibrium equations. We will use two equilibrium equations. First equilibrium equation is sigma m is equal to 0 about tension reinforcement. Now, the total compression generated by concrete is the area of the stress block into the breadth of the section. Area of the stress block, rectangular cum parabolic stress block is 0.36 FCK into HU into breadth of the section. That comes to 670 kilonewton. Now, this is the stress strain in the compression reinforcement calculated by direct proportion. Corresponding to the strain value of 0.027, we get the stress in compression reinforcement as 410 Newton millimeter square. This can be obtained in page 6 of SB60. Now, the concrete occupied by the reinforcement is already considered. We have to avoid the duplication. Therefore, we will deduct the stress in concrete, which is the ST fiber stress of 0.55 FCK, to be deducted from the compressive stress of compression reinforcement. That comes to 410 minus 0.45 into 25. It comes to 399 Newton millimeter square. This is the net stress in the compression reinforcement. Now we will come to the equilibrium equation sigma m is equal to 0. Now this external moment is acting in the clockwise direction. The moment of the external compression, if you take about T, it is also acting in the anti-clockwise direction. The moment generated by the external moment is acting in clockwise direction. The moment due to compression is also acting in clockwise direction. This is 170 kilonewton. This is the tension reinforcement. If you take moment about this tension steel for this 170 kilonewton, it is clockwise moment. These two are causing clockwise moment. The moment generated by C1 is anti-clockwise. The moment generated by compression reinforcement C2 is anti-clockwise moment. Anti-clockwise moment should be equal to clockwise moment, so that sigma m is equal to 0. That is what we have written here. This is the external moment. This is the external moment due to compression, and this is the arm distance. This is the external compression. Arm distance measured from tension steel. This is the compression generated by concrete, and this is the arm distance of C1, and this is the magnitude of C1, and C2 is the compression generated by reinforcement. This is the arm distance for C2. In this equation, C2 is the only unknown. You can easily solve it. It comes to 289 kilonewton, and therefore ASC comes to 289 kilonewton divided by the stress in the compression reinforcement. It comes to 724 millimeter square. And now you can decide the numbers and diameter of the bars. Now we will proceed to the other equilibrium equation. Sigma H is equal to 0. Here, the two forces, external compression and internal tension, these two are acting towards right. The internal forces, C1 and C2, these two are acting towards left. The forces acting towards left should be equal to the forces acting towards right. So that sigma H is equal to 0. 170 plus T. These are the two forces acting towards right. C1 acting towards left, C2 acting towards left. This is C1 and this is C2. In this equation, T is the only unknown. T is equal to 789 kilonewton. And the stress in the tension reinforcement is 0.87 F5. Therefore, AST comes to 425 torque. This design is economical because we have assumed the concrete under compression to the extent of 0.46 D. Now, how to get the solution so that ASC is equal to AST? The solution for ASC and AST is not unique. You can assume several values for XU, and for each and every value of XU, you will get one value of value for ASC and AST. For example, if you are assuming the XU in the range of approximately 0.2B, then you will get ASC is equal to AST. Here the solution is not unique. You can assume any value for XU. Here we have assumed this as a balanced section so that the concrete is utilized to the maximum extent possible. It cannot be allowed beyond 0.46D. We have assumed up to 0.46D as a balanced section. You can assume any value for this XU, and for each and every value. For example, if you are assuming XU on the lower side, the compression generated by concrete will be more, and accordingly the value of C2 will work out more. Compression reinforcement will be more. When you are assuming XU in the range of 0.2D, the compression in concrete is less. Accordingly, the compression to be carried by the reinforcement is more. Correspondingly, the reinforcement in the compression zone increases. As a result of which, you will get compression reinforcement steel and tension reinforcement steel. Both are equal when you are assuming it in the range of approximately XU is equal to 0.2D. For this, I have given one example, which I am quoting in the following reference material. And now, my request is, please follow this in practice, number one. Number two, when you are using the software for the inbuilt design, you please ask for the validation from the software provider. Check whether it is in line with the equilibrium equations and compatibility equations. And in my opinion, this is not addressed in SB16 or IS 456 so far. I have already written to Professor Murthy of IIT for incorporation in revision of IS 456. You also please take it forward. And this strain in compression reinforcement will be generally in the range of 0.8 Fy. As against the strain is the value of tension reinforcement, which is in the range of 0.8 Fy. Stress in the tension reinforcement will be 0.87 Fy. Stress in the compression reinforcement will be 0.8 Fy. Instead of calculating the strain, we can as well take straight away the stress in the compression reinforcement as 0.8 Fy as against the stress in the tension reinforcement, which is in the range of 0.87 F. Once you did this approximation, we can easily develop a formula also. That formula is also given in the coming reference material to be quoted now. Now, my request is, please visit this YouTube channel RGM class. In this YouTube, below the YouTube, there will be one icon R. If you press that icon R, it will lead to RGM class where all my videos are listed. Now, this is the blog material, design of RCC flexural members subjected to predominantly bending and low value of compression or tension. Just now we have discussed the case of a member subjected to predominantly bending and compression and calculation of ASC and AST. Similarly, I have done analysis problem also, where we can calculate the maximum moment that can be resisted along with the associated axial force, so that it can be compared with the given bending moment and factor of safety can be arrived at. Analysis problems are also addressed in this blog. And similarly, tension case is also addressed in this blog. And there is one more blog material where all the analysis and design problems are addressed, that is titled as Stress and Strength Analysis of RCC members. So this blog material as well as the other detailed blog material, Stress and Strength Analysis of RCC members, are available in my website, which is https://rgmsite.wordpress.com. This is my website. All my blog materials are available in this website. Please visit my website. I also request you to give your comments in this YouTube channel. Thank you all.